Before we dive into our next lesson, I thought this would be a good time to go over all the rules to live by that we've seen so far. As I've suggested in the past, it is a good idea to have a list of the rules separate from your notes that you can reference as needed to solve questions. As we learn more rules, you'll find that they sometimes stack on each other, and in fact, we're going to see one of those in this lesson that's coming up. So, what do we have so far? Well, the very first one that we looked at was this definition of derivative way back in Unit 1. And this basically tells me that f prime of x is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. This is the limits one. It is a general rule that shows the proof of why the derivative rules work, but it can be tricky to work with as there's a lot of moving parts with having to expand, factor, simplify, eliminate, substitute. You get the picture. In the last lesson, we added 4-ish rules to the list. It's really 5, but I combined one of them together. These make finding the derivatives in certain circumstances much easier. So the first one of those that we looked at was this number 2, the constant rule. And it's telling me that if f of x is just equal to some number c, then the derivative of that, f prime of x, will always be equal to 0. Then we had the power rule. So this one tells me that if f of x is equal to x raised to some power of n, then the derivative f prime of x is going to be equal to n times x raised to the power of n minus 1. So we're bringing the power down in front. So we bring the power down in front, and then we're subtracting 1 from the power to get our final degrees for that function. So I've just popped a little example in here. So if we have f of x is equal to 3x cubed plus 5x squared minus 6x minus 7, I'm going to start with this first one, 3x cubed. I'm going to take my power of 3 down, multiply that by the 3 to get 9x, subtract 3 minus 1 to get 2, so 9x squared. Now I have 5x squared, so 5x squared. I'm going to take the 2, I'm going to bring it down. 2 times 5 is 10 times x, and 2 minus 1 is 1, so I don't have to put anything there. Then, I don't want you to think that we need to there. I'm going to get rid of that because I don't want you to think it's to the power of 0. Then, when I have 6x, this is to the power of 1. 6 times 1 is just going to stay negative 6, and the x disappears. And then our negative 7 follows that constant rule. The derivative of any constant is just 0. So our derivative for this equation would be f prime of x is equal to 9x squared plus 10x minus 6. The next one that we have is the sum difference rule. And this one is just really telling me that if I have some function that's just two other functions added together, then the derivative is just going to be the derivative of both of those functions added together. And the same thing happens if I'm subtracting. So when I have the difference between two functions, like f of x minus g of x, then my derivative is just going to be the derivative of f of x subtract the derivative of g of x. And then we had one last one, was that constant multiple rule. And the constant multiple rule tells me that if I have, if my function f of x is equal to some constant times another function, then my derivative is really just going to be that constant times the derivative of that function. So we're going to add 2 more rules to our list in today's lesson, the product rule and the power rule of a function, which is a special case of another rule that we're going to see in the not until the next unit. So pause this and make sure you have all of these written down somewhere, and then we're going to carry on with today. So how do you find the derivative of a polynomial in factored form without expanding it? So here's an example. We have y equals x plus 2 times 2x minus 3. We could take the derivative. Could you take the derivative of each set of brackets individually and multiply your results? Let's try it. So if I have my derivative of x plus 2, well, my derivative of x plus 2 is just 1, and my derivative of 2x minus 3 is just 2. that would give me a derivative of 2. This doesn't really make sense if we think about it. Remember, the derivative represents the slope of the tangent. So x plus 2 times 2x minus 3 is not a linear function, it's parabolic. So the tangent would be represented by a linear equation, not just y equals 2. I want to draw that graph just so you can take a peek at it and see what we have going on here. And I'm just going to draw it small, but I just think it's important to see it. So here's my graph. So I've got my parabola, and it's going to pass through somewhere over here at -2. It's going to come up through here. It doesn't really matter. I just want you to see. So there's the parabola. So it really wouldn't make sense if the slope of the tangent at all points along here would be equal to 2. So we can see that if I try to take the tangent at any point, it's not always going to be equal to 2. In fact, the slope of the tangent would be changing as we move along the curve. So on this left-hand side, as we're going towards the vertex, my slope will be decreasing, which means that if I were to draw the graph of the tangent on here, it would be going down and to the left. And as I'm coming from the vertex up this way, my slope is increasing, so my slope of my derivative, or my graph of my derivative, is going to be up and to the right. So that method won't work. So I think I've just explained that to you. So explain why this answer doesn't make sense. Well, this is because, let's put some of that down in words. So that's because x plus 2 times 2x minus 3 is parabolic. And it wouldn't make sense for it to have a straight line like this as its derivative. So f prime of x, and I'm going to put a little question mark there because it really isn't what it should be. What else did I want to tell you? So with this, we know that it would be linear. So the tangent would be represented by a linear equation, not just y equals 2. Would be a linear equation, not just y equals 2. So now, let's try expanding the original equation and then taking the derivative. So we have x plus 2 times 2x minus 3. We're going to use the distributive property to expand this out. We get 2x squared minus 3x plus 4x minus 6. We're going to collect like terms, and that leaves us with an equation of 2x squared minus x minus 6. Now, this is not the derivative. This is just the expanded equation. But I know how to take the derivative of this without having to do any mathematical gymnastics. I'm just going to use my power rule and my sum and difference rules. So my derivative of 2x squared, take my power, move it down, is 4x. My derivative of x will just be minus 1. And my derivative of negative 6 is 0 because that's the constant rule. So this would be the equation for a linear function, and this is what we were looking for. This is the correct answer, and this leads us to our next rule to live by. This rule is the product rule, and it basically says that if both f and g are differentiable, so I can differentiate both of them, it is possible, then so is f times g, or the product of that. So in our regular notation that we've been doing, it just says that f times g, the derivative of that, will be equal to, and I'm going to write this slightly differently because I like to say it slightly differently than this. It's going to be equal to the derivative of the first, which is our f prime of x, times our second function, plus the derivative of the second function times the first function. So derivative of the first times the second plus the derivative of the second times the first. Now, we can also write this in Leibniz notation. That would give us d over dx. And remember, these mean the same thing, is equal to f of x d over dx, so the derivative of f of x times our function g, plus the derivative of our function g times our function of at f. This is really, like I say, just saying the same thing. So when we're multiplying two functions together, the derivative will be the derivative of the first times the second plus the derivative of the second times the first. So let's write that out. So the derivative of the first times the second function times the second plus the derivative of the second times the first function. Okay, so let's look at an example. So determine if f prime is equal to 1, so at f prime equals 1, if f of x is equal to x plus 1 times x squared minus 2. And we're going to do this two different ways. We're going to do it by expanding it, and we're also going to do it by using our new product rule. We're not going to use Desmos right now. So let's look at expanding it. So I have x plus 1 times x squared minus 2. We're going to use our distributive property to expand this out. So I end up with x cubed minus 2x plus x squared minus 2. I'm going to collect my like terms, and that leaves me with x cubed plus x squared minus 2x minus 2. Now, that is not my derivative. That is just my expanded function, right? So now I'm going to use my power rule and my sum and difference rules just to go ahead and find the derivative of this. So this would be 3x squared plus 2x minus 2. There is my first derivative, my derivative. So now the question, we're not done yet though, because the question is asking us to find when x equals 1, basically is what this is doing. So we are going to sub x equals 1 into our derivative. So if f prime at 1 is equal to 3 times 1 squared plus 2 times 1 minus 2, that gives us 3 plus 2 minus 2. So when x equals 1, our derivative is equal to 3. Now let's do it using the product rule. So we have f of x is equal to x plus 1 x squared minus 2. And this is where this f and g is going to come in. So you'll notice I've put a capital F here now. That's not super important, but I'm going to treat this as my small function f, and I'm going to treat this second one as my small function g. So we're going to find the derivative for each one of those polynomials. So I want to know, what is f prime of x? Well, f prime of x is just equal to 1. Well, what's g prime of x? Well, g prime of x, of this one here, is equal to 2x. End of discussion. So now we're going to use the product rule and we're going to put it all together. So just as a reminder, my product rule tells me that this derivative is going to be equal to the derivative of the first times the second plus the derivative of the second times the first. So now let's fill that in. So my derivative of my first function is just 1. So I have 1 times my second function, which is x squared minus 2. And I'm going to add that to my derivative of my second, 2x, times my first function, which is x plus 1. So this leaves me with x squared minus 2 plus 2x squared plus 2x. I'm going to collect like terms again, and that gives me my derivative of 3x squared plus 2x minus 2. Same as what we got over here, which is good because that's what we were aiming for. Same process as before. We're now going to sub x equals 1 into here. So when f prime at 1, we have 3, 1 squared, plus 2 times 1 minus 2, also gives me an f prime at 1 value of 3. And remember that this is the slope of the tangent when x equals 1. So on this equation, that's what we found here. So f prime is equal to the slope of the tangent at any point on the graph. So what we have found is that when x equals 1 on the original curve, the slope, or the instantaneous rate of change at that point, is 3. The product rule can be used for any number of polynomials that are multiplied together to get the derivative. And here's what that would look like in general for 3 polynomials. So it doesn't matter how many polynomials we have that we're multiplying together, the general rule is going to stay the same. So my p prime of x, or my derivative of p, is going to be equal to the derivative of the first times the second 2, so f prime of x times g of x times h of x, plus, now I've got my derivative of my second. I'm just going to write it slightly different. So f of x times my derivative of my second, so g prime of x times h of x. And then finally, I'm going to have f of x times g of x times my derivative of that last function. So that rule doesn't change. You're still taking the derivative of the first times the second and third. Then you're going to take the derivative of the second times the first and the third. And then you're going to take the derivative of the third times the first and the second. Let's try a question. So this question is asking us to find the derivative of y equals x plus 1 times x plus 2 times x plus 3 and the equation of the tangent line when x equals 1. To find the equation of the tangent line, we need 3 things. We need to know our x1 value, which we already know. We know that x1 is equal to 1. We need to know our y1 value, which we can find by substituting x equals 1 into the original equation. And we need to know the slope, which we can find by finding the derivative and then substituting x equals 1 into the derivative, because the derivative is actually equal to the slope. So let's start by finding y equals 1. So let's find y1, sorry. So to find y1, we're simply going to sub x equals 1 into the original equation. So sub x equals 1 into the original equation. This is just giving us a point. That's really what we're finding here, is the point. So we have y equals, or f of x is equal to. So I'm just going to sub in. So 1 plus 1 times 1 plus 2 times 1 plus 3. That gives me 2 times 3 times 4, which is equal to 24. So what this is telling me then is that my y1 value is 24. Now let's find the derivative so we can use it to find out what the slope is when x equals 1. And I've said this already, but I'm going to say it again. The derivative is the equation for the slope of the tangent. So if we find the derivative, we can use it to calculate the slope. So here is our equation. We have f of x is equal to x plus 1 times x plus 2 times x plus 3. Now we have three three equations we're multiplying together. I have f, g, and h. My process is going to be exactly the same as what I just did on the other slide, just in general terms. So my derivative of f of x is just equal to 1. My derivative of g of x is also equal to 1, and my derivative h of x is equal to 1. All I did was I looked here and I said, okay, it's all equal to 1. So now I'm going to use my product rule, and I will get the derivative of the first times the second times the third plus the derivative of the second times the first times the third plus the derivative of the third times the other two. So now we're going to start filling this in, and I'm hoping I've left myself enough room here. So let's deal with this part first. So f prime of x we said is equal to 1, and that's just times the other two equations. So x plus 2 times x plus 3. Now let's deal with this one. I have f of x is 8x plus 1. My derivative of g is just 1 times h, which is x plus 3, plus, now we're going to do this one. We have f of x is x plus 1, g of x is x plus 2, and the derivative of h is just equal to 1. We're going to expand all this out, and then we're going to collect like terms. So when I expand all this out, I get x squared plus 3x plus 2x plus 6 plus x squared plus 3x plus x plus 3 plus x squared plus 2x plus x plus 2. Now, this is where you might be saying, you do have to be a bit careful when you're expanding and making sure that you're collecting everything you can. So I have x squared plus x squared plus x squared. That's going to give me 3x squared. Now let's take a look at my x's. I have 3x and 2x and 3x and x and 2x plus x. When I add all that together, I get 12x. And then I'm going to look at my numbers. I have 6 and 3 and 2. I can add those all up to give me 11. So my derivative is 3x squared plus 12x plus 11. To find the equation of the tangent line, remember I said we needed three things. So now we need to substitute 1 into our equation to find out what our slope is. So my slope is equal to 3 times 1 squared plus 12 times 1 plus 11. And that is going to be equal to 26. So now we're going to put this all back together and create our equation. And in order to do that, we're going to use the point-slope form. So use point-slope form. And just as a reminder, that's y minus y1 equals m times x minus x1. And we're just going to fill in what we know. We know y1, we know m, we know x1. So we know that this is y minus 24. Just going to fill that in, that's 26, equals 26 times x minus 1. We're going to expand, we're going to rearrange. So we end up with y equals 26x plus 23. There is my equation. We have finally answered the question. The equation of the tangent line when x equals 1 will be y equals 26x plus 23. Let's look at another rule to add to your list. This one allows you to differentiate any polynomial without multiplying out the brackets, which, as you can imagine, could come in handy. This new rule is called the power of a function for positive integers. So let's determine f prime of x, given that f of x is equal to some other function g of x squared. Instead of expanding out the function g of x squared by doing g of x times g of x, we'll use our power rule to move the power down, and then we're going to multiply it by the derivative of what's inside the square brackets. So f prime of x is going to equal, I'm going to bring this power down in front, so it's going to equal 2 times our function, what's inside the square brackets. 2 minus 1 is just to the power of 1. And then I'm going to multiply it by the derivative of whatever's inside the brackets. So in this case, in general terms, that's g prime of x. So our derivative is f prime of x is equal to 2 times g of x times the derivative of x. This works no matter what the power is. So here's another example. Determine f prime of x given that f of x is equal to g of x all raised to the power of 3. We're going to do the exact same thing for this one. We're going to bring the square down in front. So f prime of x is going to be equal to 3 times g of x, 3 minus 1 is 2, so that's raised to the power of 2, times the derivative of whatever's inside the brackets. In general, this rule can be stated as if f of x is equal to some function g of x all raised to the power of n, then f prime of x is equal to n times g of x raised to the power of n minus 1 all times g prime of x. So let's look at a couple of examples that's going to use our new rule. So the first part of this example is asking us to find the derivative of y equals 3x minus 1 to the power of 5. We're going to use our new rule to sort this one out. And I want us to think of this as f of x is equal to 3x minus 1 all raised to the power of 5. So that's how we're going to think of it. So we're going to find the derivative of g of x. So g of x, that part in the middle, there's my g of x, that part in the middle is 3x minus 1. So that means that the derivative of that is just equal to 3. Now we're going to use our new rule and put it all together. So remember, our new rule is telling me that f prime of x is going to be equal to n g of x raised to the power of n minus 1 all times the derivative of whatever's on the inside. That is going to equal, I'm going to bring my power down, so 5 times 3x minus 1 raised to the power of 4 times my derivative of what's on the inside, which is just equal to 3. I can multiply 3 times 5, which gives me my derivative f prime of x of 15 times 3x minus 1 to the power of 4. This next one combines the power of a function rule and the product rule. So we have y equals 2x plus 1 cubed times x plus 2 squared. And I have to find the right piece of paper because I have been working on this one for a little bit. So we're going to label this one G and we're going to label this one H. So I'm going to take my derivative. So g prime of x, that's this one here, is going to be equal to 3 times 2x plus 1 squared times the derivative of what's on the inside. That's times 2. So this gives me 6 2x plus 1 squared. So I've used my new rule. I've gotten my derivative of g prime, or g prime of x. Now let's do the same thing for h. So h prime of x is going to be equal to, using our new rule, I'm going to bring the power down, 2 times x plus 2. 2 minus 1 is just 1. I don't have to write anything here for the power. Then I'm going to get rid of that so we don't get confused about that. X plus 2, and I'm going to multiply that by the derivative of what's on the inside. That's just 1. So h prime of x is equal to 2x plus 2. That's only part of it. Now we have to put it all back together using our product rule. And just as a reminder, the product rule, when we're multiplying two functions together, tells me that f prime of x, or the whole thing, is going to be equal to the derivative of the first times the second plus the derivative of the second times the first. That's why we took the time here to find these derivatives, because we need them now. So this is going to equal the derivative of my first one, so 6 2x plus 1 squared, times my second one, the whole thing, x plus 2 squared, that's my h, plus the derivative of my second, 2x plus 2, times my whole first one, which is this one here, 2x plus 1 cubed. And that is our answer. So f prime of x is equal to 6 times 2x plus 1 squared times x plus 2 squared plus 2 times x plus 2 times 2x plus 1 cubed. Okay, that's a lot, and I think it's important that you practice. So there is quite a bit of homework. Here's the homework for today. It seems like a lot, but the more practice you do, the more ingrained these new skills will become. There's also an exit ticket for today, so once you've completed the homework, you should give that a try. As always, reach out by email if you have any questions.